Good afternoon. I welcome to this session of experimental methods in fluid mechanics. This is in continuation of my last lecture where we have discussed about the measurement of flow. In particular, we have seen that how we can measure volumetric flow rate of an incompressible liquid. In fact, we have discussed about the volumetric flow rate measurement of an incompressible liquid and using and flow obstruction flow rate measurement. We have worked out that how by providing by placing an object of any shape we can disturb the flow field, which will eventually leads to a drop in pressure, and by measuring the drop in pressure we can calculate the flow velocity. From there we can calculate the flow rate through either through analytical expression or using empirical relationship. Now, we also can measure the flow rate or the volumetric flow rate of the compressible fluid and using the same principle, and as you have seen that if we try to measure flow rate, volumetric flow rate using flow obstruction instruments, like the instruments which are used to provide obstruction to the flow field, from there we can measure flow rate. For that we have seen that we have applied continuity equation and then we have applied the Bernoulli equation, but consideration of Bernoulli equation is not the actual, rather it is not the realistic one. In fact, the fluid is not inviscid, but considering Bernoulli equation, the pressure drop that we have calculated through analytical calculation or procedure, and we have equated the pressure drop which we have measured experimentally using the U-tube manometer. Now, since we have considered inviscid flow essentially to apply Bernoulli equation to measure the pressure drop theoretically, the theoretically measured pressure drop and won't give us the correct measurement of the volumetric flow rate, rather it will overestimate. Now, to get the actual flow rate we have multiplied that actual flow rate with one coefficient which is near very close to 1, but not exactly 1, and that value CD, coefficient of discharge, can be obtained by calibrating through calibration process, and this technique is there in most of the undergraduate textbooks where we can have flow rate measurement using venturimeter, orifice meter, and even then we have discussed briefly. But the same thing can be measured using for the compressible fluid, and for that we need to consider the fluid is frictionless, I mean isentropic flow, adiabatic and frictionless flow, but it may not be the case that the fluid is always frictionless because viscosity is there, so viscous effect will be there. So, eventually when you will come up with the expression of the volumetric flow rate, that should be multiplied by one factor, but that part I am not going to discuss here. So, today we will see that again how we can measure flow rate. So, flow measurement is nothing but the measurement of volumetric flow rate or mass flow rate, or it may be the point velocity measurement or determination of the flow streamlines. That is what we have discussed in the last lecture. So, today we will see that rotameter is also another instrument which is used to measure flow rate in a flow field. So, we will see through a schematic depiction, rather we will see the principle by how we can measure flow rate using rotameter and the principle on which this instrument works, and finally what are the precaution we need to take into account while we are using this rotameter to measure mass flow rate or volumetric flow rate of the fluid in experiments. So, today we will discuss about the rotameter. So, this rotameter is also a flow meter, and this is used to measure flow rate. Now, important thing to note here that we have discussed in my last lecture that is flow obstruction flow rate measurement, and this rotameter works on the principle that it uses drag. So, now I will be drawing the schematic. So, the rotameter, I can write the rotameter is the flow meter that uses drag to measure flow rate. So, in the last lecture we have seen that by placing an object in the flow field, we can disturb the flow field and that will result of drop in pressure. Now, this meter works on the principle that it uses drag to measure flow rate. So, we will see by how we can measure the flow rate using this flow meter. I can say this meter then works on the physical principle of drag. Now, if I draw a schematic, the schematic will be the schematic will be helpful to explain the principle, rather the measurement principle and the analytical calculation which is required to know ultimately the flow rate which we will get using this flow meter. So, I can draw a schematic depiction of the flow meter, that is rotameter. Rotameter. So, and there will be one bob the corner won't be sharp, rather the bob, and the maximum diameter of the bob is say small d, and diameter of this, so essentially this is d. So, the rotameter is essentially what I can say, that what we can see from this figure is essentially a tapered, it is a composed of tapered tube which is vertical, and one bob is there, the diameter the maximum, this is bob. So, this is bob. So, this rotameter is composed of a tapered vertical tube and a bob which is placed in the tube. Now, small d is the maximum diameter of the bob, and capital D is the diameter of the tapered tube at the bottom. So, diameter of tube at bottom, or I can write inlet. So, flow is taking place from the bottom, and this is inlet and this is outlet. So, this is inlet, right. Now, when there is no flow, then bob will be at rest. So, when there is no flow, bob will be at rest, and rather bob will be at the bottom of the rotameter. So, no flow through the tube. So, this entire system is known as the rotameter, and the bob is having weight, say this is y direction, this is y direction, and the bob is having weight, say I can write m, weight of bob is m. Now, this is the flow direction. So, this is the flow direction. Now, just when we start flow from the bottom, so the flow will try to keep the bob, rather will try to drag the bob along, and it will be in the fluidics, I mean the bob will be in the fluidized state. So, when there is no flow, bob is at rest, and it will be no flow through the tube, bob is at rest, and at the bottom of the rotameter. Now, a vertical flow, say a vertical flow is flowing through the tube. If we consider the velocity of the flow is um, say vertical flow velocity, velocity is um, and vertical flow velocity I can write between the tube and bob. So, this vertical flow between tube and bob is um. So, when a flow is there from the bottom of the rotameter, the flow will try to push the bob along, rather the flow will try to drag the bob along, and it will try to push the bob upward. And if we consider the vertical flow velocity between the tube and the bob is um, now a vertical flow which is provided at the bottom will try to push the bob until the mean flow between the mean vertical flow between the tube and bob is equal to the um, because such that the vertical drag. Now, question is, this is the mean vertical velocity. So, this is the mean vertical flow velocity between tube and bob, and if I go to the next slide, then if I write that, now say when the flow is there from the bottom, so it will push the bob upward, and the bob will be taken by the flow, rather the flow will drag the bob along until and unless the mean vertical flow velocity between tube and bob is um, such that the drag force due to um just balances the bob weights as the buoyancy. So, I am writing that vertical flow pushes the bob up until the mean flow velocity between bob and tube wall or tube is equal to um. So, and such that the vertical drag, because this instrument works on the principle of drag, vertical drag force due to um just balances the Bob's weight and the buoyancy. So, if I go back to the previous slide, then there will be a mean vertical flow between the bob and the tube, and since the flow is continuously flowing, the fluid is continuously flowing from the bottom to the top, then initial flow will try to push the bob along and it will try to push the bob up, and this movement will continue until the mean velocity between the bob and the wall is such that, and this condition will be reached when the vertical force due to that mean velocity will balance the bob's weights and the buoyancy, right. So, that means from this discussion we can say that the position of the bob in the tube is an indication of the flow rate, because the mean flow between the bob and the tube and the drag force due to this mean flow, that will balance the bob's weight and the buoyancy. So, eventually the vertical flow will try to push the bob and this movement will continue until this is attained, and what for the for which the buoyancy as well as bob's weight will balance with the drag due to that So, the position of the bob, so the movement will continue or the upward movement of the bob will continue until that height where the uniform velocity, rather uniform mean velocity between bob and tube, the drag because of that uniform velocity between bob and mean velocity between bob and tube will balance the bob's weight and the buoyancy. So, this is very important, that means position of the bob in the tube will be, rather is an indication of the flow rate. Now, if I try to write a force balance, so what I can write? So, thus the drag force we can write CD into A into rho F into square by 2. That means the here rho F is the density of the fluid, and this drag force, if I write the force balance, this drag force is nothing but G into VB into rho B minus rho F, and that is F, this I can write VB, the total volume of the bob. So, this force balance FD, this is nothing but I can write Fg minus Fb. So, Fd, this is nothing but Fg minus Fb. So, the movement will continue until the location, in that location the uniform velocity, rather the mean velocity between bob and wall will be responsible for the drag force, and the drag force will be balanced by the bob's weight and the buoyancy force. So, this is the where, and this A in this expression, A is the frontal area of the bob, and the subscript F's denotes fluid and the subscript B denotes bob. Now, so if I know, that means, now question is the this mean velocity, because as I said that if I go back to my previous slide, that the position of the bob in the tube is an indication of the mean flow rate. Now, this qm, I can write this qm, q is equal to A into um. See, this is the mean velocity, is the vertical mean flow velocity between the tube and the bob, and this area, this A is area of what? That area is obtained from the quadratic area relation. So, the area is obtained from the quadratic area relation, and this A is pi by 4 d plus AY plus square minus small d square. So, d plus AY square plus small d square, where A is equal to constant which depends upon the tube taper angle, tube taper. So, A is equal to constant and which depends upon the tube taper. So, the flow rate cube is equal to pi by 4 d plus AY square minus d square into and from there we can calculate the flow rate, right. Here a few important things that I will discuss now. That the important is that when the flow is taking place from the bottom, there is a flow velocity, and that flow velocity will try to drag the bob along. How long that flow velocity will try to drag the bob along, that will depend upon the strength of the flow velocity. Now, as I said that the position of the bob in the tube is an indication of the flow rate. That means bob elevation, because bob will be lifted by the fluid velocity from the bottom. Now, the elevation, the bob elevation, which is dependent on the annular area between the bob and the taper wall. Now, which is other way, that the fluid velocity will try to push the bob, and depending upon the strength of the fluid velocity, that is what we need to calculate, because we need to calculate the flow rate. So, we will calculate the flow rate through the pipe or any fluidic confinement, where we have used this, where we need to install this flow meter. Now, by the strength of the flow velocity, the bob will be pushed off and it will stop certain location. Now, at that location, what is the mean velocity between the bob and the tube, and because of that mean velocity there will be a drag, and the drag force will try to the drag force will be balanced by the bob weight as well as the buoyancy force, and by balancing these two we have calculated what will be the flow rate, and for that we have just calculated the area that using the quadratic area relation, and that is very simple, and where A is constant and that will depend upon the tube taper. Now here I can tell that this bob elevation is dependent on the annular area between it and tapered tube. So, now the annular phase. So, all things are related. Now, we can say the to have the same flow rate measurement, if the annular phase is the gap between the tube and the bob is not very large, then we will get one kind of bob elevation, but if it is too large, then we will get another kind of bob elevation. But whatever will be the bob elevation, now bob elevation is important because it will give an indication about the flow rate. So, and that will also depend upon this. Whatever will be the bob elevation, at that elevated level there will be a mean velocity, and for that there will be a drag, and we know the frontal area of the bob, and that because of that drag, the drag will be balanced by the bob weight, because the natural tendency of the bob will be try to remain seated at the bottom. So, that weight plus the buoyancy force, that will be balanced by the drag force. From there we have calculated the flow velocity, and knowing the mean flow velocity we can calculate the flow rate by knowing this, because we can calculate by, because we know this Fg and we can calculate the Fb. So, here I can calculate because the expression of Fd is having Now, Fg, that we know the bob weight, and the buoyancy force because we know the bob volume and also the fluid density. So, from there we can calculate using this expression. From there we can calculate the volume flow rate. Now, two important points that I would like to mention over here, that the flow rate which we have obtained is very important, that because the entire calculation is based on the drag. Now, we know the drag is dependent upon the Reynolds number, and that also will depend upon the fluid viscosity. So, when we are designing the rotameter, when we are using this rotameter, the fluid viscosity plays an important role to calculate this drag. And it is also important to note that our measurement should not have any bias, should not have any dependent on the fluid density as well, because if we need to ensure that our measurement, rather the measurement process using this rotameter should not have any bias, should not have any dependent on the density, this is an advantageous feature, and that can be obtained by doing small calculation. By how? Because we have calculated the flow rate, volume flow rate. Similarly, we can calculate the mass flow rate. Now, mass flow rate can be calculated from the volume flow rate. Now, if we need to know that the measurement should not be dependent on the fluid density, then just simply we can make the mass flow rate, the partial derivative of mass flow rate with respect to the fluid density equal to 0, and from there we can calculate what will be the, knowing the bob density of the bob material, what will be the density of the fluid, rather, which is other way true, that if I know the density of the fluid in which we need to install this rotameter, from there we can calculate what will be the density of the bob material, and also we can calculate the elevation of the bob, knowing the fluid velocity typically which will vary from this range to this range, and so that the design can be optimized. So, what you have understood, that This simple instrument, which is very commonly used to measure the flow meter in most of the industrial applications, and also in the area of experimental research, to measure the flow rate, and similar to the flow obstruction flow rate measurement technique, this measurement technique, this instrument works on the principle of that it uses drag. Now, whenever we are placing any material, any object, any object of any size in the flow field, of course this is free. I mean, it will try to, the flow velocity will try to drag the bob along, but it will try to the flow velocity will try to push the bob up to a certain height. Now, that height is restricted by the fact that because the bob is having weight and also buoyancy will be there. So, these two force will be balanced by the drag force. From there we can calculate the velocity, because drag force, which is related to the fluid velocity, mean velocity of the flow between tube and the drag, and from there you can calculate volume flow rate, knowing the area, and that area also we obtain from the quadratic area relation, and knowing the flow rate we can calculate mass flow rate. And very important that the measurements should not be biased, rather measurements should not be dependent on the fluid density to ensure that we can calculate the relationship between the density of the bob material and the fluid density. And also one important thing, that drag is highly dependent on the Reynolds number, which is also dependent on the fluid viscosity. So, I mean, by knowing the fluid viscosity we can also control, or we can modulate or tune the drag which is being applied on the bob. So, to summarize today's discussion, we have discussed that we can measure flow rate using different instruments, that is venturimeter, orifice meter, and these two types of instruments, I mean venturimeter and orifice meter, their operational principle, their operational principle is same. This is flow obstruction flow rate measurement technique, and what we have seen, that just knowing the drop in pressure because of the change in the change in the shape of the fluidic pathways, we can calculate the pressure drop theoretically. And if we have equated that pressure drop with the experimentally measured pressure drop, from there you have calculated velocity using the Bernoulli equation, and if we know the velocity, from there we have calculated area, because we know the area through which the fluid is flowing, I mean the throat area. Now, and again we have seen that there are a few assumptions, because of these assumptions the calculation is not the actual one, and to have the actual value we have to multiply with a factor, and that is the coefficient of discharge. Now, today we have seen that using other instrument, that is rotameter, which works on the principle of drag, we also can calculate the flow rate, but there are a few restrictions that depends upon the taper and the distance between, the gap between the wall of tube and the bob, and our measurements should not, to ensure that our measurements should not have any bias with the density of the fluid as well as viscosity of the fluid, we need to take up precautions. So, with this I stop my discussion today, and we will continue our discussion in the next class. Thank you.